When the path along which a particle travels is known, such as this blue path here, it is often convenient to describe the particle's motion using a normal tangential or NT component system. We will now study kinematics of curvilinear motion in the context of normal and tangential components. We will restrict our study to two-dimensional motion, that is, motion within a single plane. Unlike a rectangular component system, which is an XY or XYZ component system, in a normal tangential component system, the orientation of the reference axes changes with the changing motion of the particle, and the origin of the NT coordinate system is always located at the particle itself. So considering this particle, which is moving along the blue curved path from its initial position O, at the instant considered, we can define the NT coordinate system, where the tangential t-axis is, by definition, tangent to the curved path. The positive t direction is always in the direction of increasing position S as measured from O. The normal n-axis is, by definition, normal to or perpendicular to the tangential axis. The positive n direction is always on the concave side of the curve toward the center of curvature O' of a differential segment of the curved path. The unit vectors that correspond to the positive t and positive n directions are denoted as u sub t and u sub n respectively. So u for unit vector, subscript t for the tangential direction, and subscript n for the normal direction. The position of the particle is measured as the distance, s equals s of t, along the particle's path measured from that reference point O. Since the particle has a velocity that is always tangent to the path of motion, its instantaneous velocity always acts in the positive tangential direction, where we have the vector v, instantaneous velocity, equals the scalar v, which would be the instantaneous speed, times u sub t, the unit vector defining the tangential direction. Here, the scalar v represents the magnitude of the velocity, which is equivalent to the instantaneous speed v equals ds by dt of the particle, which we can write in dot notation as the scalar v, the instantaneous speed, equals s dot, which, as you recall from earlier in chapter 12, that s dot is equivalent to ds by dt, one dot for the first time derivative. The instantaneous acceleration of the particle is defined as the time rate of change of velocity. So the vector a, the acceleration vector, is by definition v dot, the first time derivative of the velocity vector. And we know that the velocity vector v can be expressed as scalar v times the unit vector u sub t. Applying the product rule, that would be equivalent to v dot u sub t plus v times u sub t dot. An analysis of the second term of the above expression is detailed on page 54 of the textbook, in which it is shown ultimately that u sub t dot, which appears here, equals v over rho times u sub n. And going back to this slide, it's important to realize what rho represents. It's the radius of curvature at the position or at the instant where the particle is being considered. And as we mentioned, v, the scalar, represents the instantaneous speed, and u sub n represents the unit vector in the normal direction. Okay, so all of this right here would go into this part here, u sub t dot. Therefore, the instantaneous acceleration of the particle is expressed as follows for this two-dimensional space, where the acceleration vector a would be equal to the scalar a sub t times u sub t plus the scalar a sub n times u sub n. We see that there is a tangential component, a sub t equals the scalar a sub t u sub t, and a normal component where the vector a sub n equals scalar a sub n times u sub n of the acceleration vector. Okay, the scalars a sub t and a sub n are defined as follows. A sub t equals v dot, that is dv by dt, that's a scalar expression. Or this one would also apply and would be useful in certain situations where a sub t ds equals v dv. For the normal aspect of the motion, the normal component of acceleration, a sub n, the scalar, would equal v squared over rho, where again rho is the radius of curvature. Okay, so in this scenario here, the particle is at this position here. Any instant in time, it has some acceleration that consists of two parts, a tangential component vector a sub t and a normal component vector a sub n. Note that the scalar a sub t, representing the tangential component of acceleration, measures the time rate of change of the magnitude of the velocity. On the other hand, the scalar a sub n, representing the normal component of acceleration, measures the time rate of change of the direction of velocity. This normal component of acceleration is often referred to as centripetal acceleration or center-seeking acceleration, as it always acts toward the center of curvature of the path of motion. The magnitude of the acceleration vector is determined in the usual way, square root of the sum of the squares of its components. So the scalar a, magnitude of the acceleration vector at any instant in time, would be the square root of at squared plus an squared. Consider some special cases of motion. If the particle moves along a straight line, then rho approaches or is equal to infinity, which implies from the equation a sub n equals v squared over rho that a sub n would equal 0 for this specific case of straight line motion. There is no normal component of the acceleration if the particle is moving in a straight line. If the particle moves along a curved path at a constant speed, then a sub t, which is equal to v dot, must equal 0, because v dot, or a sub t, representing dv by dt, measures the time rate of change of the particle's speed. If there is no change in the particle's speed, then that a sub t component would have to be equal to 0. So shown here, we have sort of a visual summary of a lot of these different things. Okay, so we have a particle increasing its speed at this instant. It has a tangential component of its acceleration in this positive t direction because it's increasing its speed, and it has a normal component of acceleration always on the concave side of the curve in the positive n direction. So this is its acceleration vector at this instant. Okay, then it's over here at some other later instant. So a sub n, as we mentioned, represents the change in the direction of the velocity, a sub t representing the change in the magnitude of velocity. So here is its overall or total acceleration vector. And then at some later time, it's now following a straight line path, at least for some finite period of time, in which case the acceleration vector would only have a tangential component, no normal component, as we stated here in special case number 1.